what we have here is a program that's written in binary. And this is for the x86 architecture. It's actually for the 8086, which was the first 86 processor by Intel that really set the trend that would dominate the next few decades. Even now, we still have processors that are backwards compatible. So they kept the 86 and they just changed the prefix. Let's imagine that your boss wanted you to make a program. Very simple. He says, what we're going to do is we have all these memory positions, right? 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6, and 1, 2, 3, 7. And there's going to be random values in the first three. And what he wants you to do is very simply add up these three and put the result in 1, 2, 3, 7. We may not do it in the most efficient way, but this will demonstrate why assembly. So let's say we have three registers that are in the CPU. We have AX, we have BX, and we have CX. And these are just the names of them. And these are 16 bits each. A simple way to do this, we're going to move the value from 1, 2, 3, 4 into AX. This is number 1. Number 2, we're going to move the value from 1, 2, 3, 5 into BX. This is number 2. Number 3, we're going to add this guy to this guy. That's number 3. And then we could say number 4, we're going to move whatever is in 1, 2, 3, 6 to the CX register. So this is number 4. And then number 5, we're going to add what's in CX to what's in AX. So this is 5. And then finally, we're going to move what's in AX to 1, 2, 3, 7. All right, so this is our program. So to do that, we have our program here, but the problem is when you wrote the program, there's a bug. What we expect to see is 5 plus 7 is 12, plus 8 is 20. So when we run the program, we're expecting to see 20, right? In 1, 2, 3, 7. But when we're testing the program, we see that the value that actually ends up in 1, 2, 3, 7 is 12, which is of course the wrong value. So we need to debug the program and figure out where the error is. So what you would do in this case, and to even write the program, you'd have these lookup tables. And I made this lookup table have only the commands that we're dealing with. Really, this would be about 70 to 100 rows long, depending on how you organize the opcodes. But what we can do is we can look at this first operand here, and we can see it's 101.0.0.0.0.1, and we can see it's the first entry here. And what this means is move data from memory into AX. So we can see our first command does correlate with moving data from memory into AX. And what we need to provide the CPU is just the address that we're talking about. And we can see that we have 2 bytes here that follow it. And this is pretty much that memory address. So we're moving to AX the value from this memory address. And there's one slight complication here. There's a format called little endian, which basically flips the bytes. So this is actually the most significant bit, which looks ridiculous. And this is the least significant bit. So this guy really follows this guy. And it's just an architecture thing. And what we can do real quick is just rewrite this in the correct format so that we can see that it actually is 1, 2, 3, 4. So I'm going to write them backwards. I'm going to write this first and write this after. 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, oh sorry, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0. And if we split these up into our hex digits, then we can see very easily that this is a 4, right? 1, 0, 0. 0, 0, 1, 1 is a 3. 0, 0, 1, 0 is a 2. And this is, of course, 1. So we see that it does say 1, 2, 3, 4. We're moving to AX, whatever is in 1, 2, 3, 4. That's this first command. So we have one command down, right? And it takes a while. So as we move through these, how on earth do you keep track of what is actually happening? I mean, are you supposed to memorize this? If you were doing this day in, day out, you're unlikely to memorize many of the opcodes. And this is a very simple program. We're only adding 3 digits together and then outputting it. So how would you even keep track of what's happening as you're going through it, line by line? Because by the time we reach down here, we're probably forgetting what this really meant. And when we're trying to find a problem, you know things are not in the right place, so you can't really assume anything, and it just becomes a sort of a nightmare. So since you're a very smart person, what you say to your boss is, hey, I'm gonna abbreviate this into a way that once I verify what the instruction is, I can make a note to myself. We have the description here from Intel of what each opcode does. Number 1, right, this is instruction 1. Let's write our abbreviated format, and we're gonna say we're gonna move. Now we don't want to write this entire sentence, although you could, but let's just say we're going to use maybe the first 3 letters as an abbreviation, and then we'll write the rest of it. So move to AX, and then we have a value here. We know it's 1, 2, 3, 4, so let's just write 1, 2, 3, 4. I think that's pretty simple. So now what we can do is forget about all this binary data, and we could just make our notes there, and then we can find the bug, hopefully. So number 2, right, what we would need to do is look up this instruction. And we can see there's an extra byte here, which suggests that the opcode itself is 2 bytes instead of 1 byte. So let's look for it here, and I put it in order to make it easy. And we can see 10001 011 000111110 is this code here, which just means move data from memory into BX. So similar to what we did. It is our step 2 here, so that is correct. Move from 1235 to BX. This is our second instruction. And then of course this address, I won't calculate it here, but it does indeed say 1235. So we're going to put move BX and we'll put 1235. So we're done with this instruction. We decoded it. Now this next instruction is 0001. And when we look it up in our binary table, we see that it means to add things together. Now this instruction seems kind of short because, as we know from just general mathematics, we need to add two things together. We can't really add one thing on its own. So why is there only 1 byte here? So we go and look at Intel's add operand table, and what we see is it's actually made up of 1 byte because it's being very efficient when adding registers together. The first 2 bits of the add operand code means that we're adding 2 registers together. So I didn't list out all the other options for the first 2 bits. I just put the one that we're using. So when we see a 1 here as in the first byte of the add operand, we know it's just 2 registers. And then what happens is the next 6 bits are just separated. So we have the type of operands that we're adding together. In this case, 1 means that both of them are registers. And then the next 3, in this case, just determine which registers we're using. So 011 we see is the BX register, and 000 is the AX register. So what we're doing in this instruction is very simply doing what we want it to do, right? At step 3 is we move, and then add BX to AX. So that's exactly what this is. So we're adding to AX the value of BX. So that's pretty straightforward. Moving on to the next one. I'm going to go a little faster because I know this is kind of tedious. So we move data from memory into CX, right? And that's this instruction. And that's also this instruction here. And then we have our address. Spoiler, it's 1236. So we write down move to CX. What's in 1236? And I started adding the commas out of habit, but really I meant for that to come later. Look at the next one. We have another add command here, right? 01. And if we look at our lookups again, we see 11 here, and we can split these up. And so we know they're both registers, and we can look up what these registers are. So 011 is BX and 001 is CX. So what we're doing here is we're adding to BX what's in CX. Now, when we look at this is step 5. If we look at step 5 here, we can find our problem. We really wanted to move what's in CX to AX, but we accidentally put the wrong bit here, right? This should be a 0, and we put a 1. So this is a bug. We're adding to BX CX, and really we should be adding what's in CX to AX. So after that, moving on temporarily, we're going to look up this command here, which is 101 00011 101 00011, move data from AX into memory. So this command just means we're going to move what's in AX to memory, which was the next step, right? Even though we had a problem here, that at least the next command is correct. We're going to move from AX into memory. We can imagine that the following 16 bits are just going to be the address. In this case, it's going to equal 1237. So we're going to move 1237, move to 1237, what's in AX. And then 7 just means to halt. If we look this up, we'd see this just means to halt the program. The point that I'm making here is by just looking at the binary, we have no idea what the problem is. And we have to go through this kind of tedious process to find the bug. And we're able to find it here. It's a pretty simple bug. We're adding, instead of CX to AX, we're adding BX. So we're basically leaving this value as what it was after only adding BX. And we need to add this other value, but we really add it here instead of adding it here. You can see a sort of language has formed here. And you could see that just by glancing at these instructions, you could find the error. We're moving this value to AX, we're moving this value to BX. We're adding them together and the result's going to be in AX. We're putting our next value into CX. We're adding it to AX and you're like, oh no, wait, this should be an AX. It's a BX. It should be an AX and it's written as a BX. So this is our problem. So immediately you can find it. This is essentially how assembly formed. It began as notes for the programmers, right? An easy way, the mnemonics, is that the way you pronounce that word? So you can pretty much read it. Like, of course, these are also human readable, but this is really like human legible. You can understand what's happening just by glancing at it. And this is the essence of binary. Now, we do have hex, of course, and we did use hex in our addressing, right? Which makes it very easy here. You can see we're combining some human readable mnemonics, that's how you pronounce it, and the hex codes to represent the memory addresses. So we're using layers of abstraction. We started with binary and then we're able to abbreviate them into hex. And now we're going even one step further and just writing these kind of words that we're able to understand when we could write the program and design it and discuss it with other people. When assembly was first made this way, when you got back to the computer, you would have to convert it to binary to input it. But the key point is that you were able to design it and write it in a way that is very easy to understand what's happening. And the only tedious part would be when you're at the computer and you're converting it back into machine code. And if you're wondering, would it be any simpler with just hex, then you would be right in some cases, in most cases. This is the same program in hex, and here's our hex code lookup. So we can see that it's pretty easy to find these commands instead of going through a bunch of zeros and ones. So A1 means move data from memory into AX. 8B1E moves data into BX, right? And then the operands follow. So in this case, 1, 2, 3, 4. And you can see they're flipped like I was talking about before. So they're not reversed, they're just flipped. So instead of 1, 2, 3, 4, it's 3, 4, 1, 2. So 1, 2, 3, 5, 1, 2, 3, 6. The only issue here is the add commands are not very easy to read, since the add commands break up the bytes out of the hex kind of form. It's 2 bits and then 2 sets of 3 bits. So it's more probably easy to see it in octal. The hex would be easy, but it's still very cryptic, of course. So after you went through this process a bunch of times, you would have an established method of writing this. And ultimately, you would end up with something that looks like this, which is the true assembly for 8086. And you can see how much more easily this is readable. The brackets just signify memory addresses. So we're moving into AX the data at this location. We're moving into BX the data at this location. We're adding BX to whatever is in AX. We're moving to CX the value at this location. We're adding what's in CX to BX. This is, of course, our bug. It should be AX, because then we're outputting AX back to memory. So as we follow this along, just to make it absolutely clear, number 1, we move this in. Number 2, we move this in to AX, BX. Number 3, we add them together, result goes into AX. Number 4, we're moving 1, 2, 3, 6 into CX, right? Move CX, 1, 2, 3, 6. The H just signifies a hex, by the way. Add CX to BX, we're adding CX to AX. Oh, here's our bug. So you cross this out, you rewrite it just as AX, and we move on. So I hope this really shows how assembly formed. And again, you know, when you got to the computer, let's say this is let's say we fix this program and we put AX. So we say, oh, we have to change this to AX, CX, right? And then we're good. When we got back to the computer, we'd have to essentially, by that time, you'd have a table, a backwards table. You would say, well, move AX from memory locations is this binary opcode. So you'd write this, you know, maybe. But at least at that point, the program itself should be proven on paper, and then you could just translate it before you write it. Ultimately, of course, we got to the point where you could write this into the computer, and it would automatically assemble it into the binary output, which I think is probably one of the most magical aspects of digital computing. That point when you can type in commands on a keyboard and it automatically translates it, assembles it to binary. We wouldn't be able to get anywhere without being able to legibly write, design, read, and test and debug programs. And assembly was a way of doing that. It's a bridge between binary and the human mind, so to speak. At least at this point in time, what you'd call rapid development. And these days, of course, assembly is incredibly error prone, and it always has been, but it's way better than binary. And then the programming languages we have now, even C, of course, which was built with assembly by Dennis Ritchie in the 70s, was light years ahead of assembly itself. So very interesting how it sort of all evolved. We began with our binary, and then we abstracted, right, some of those details to hex, and this would be easier to read than the binary. And then, of course, we abstract this even more, and we just create these short human legible type commands. We can call them tokens or symbols. So this is how it evolved, and this is a simple program, but we can see how long it took to find a bug. So imagine something like the Unix operating system that at first was written in assembly. It's just absurd to think, and these guys really were geniuses to develop all of these things that we kind of take for granted now. So this is how it formed. This was the need. You can't really keep track of this very easily, so you have to make your notes, and then it's like, well, why not write it this way and then translate it, reverse the process, right? So this was the birth of assembly. I hope this helps to answer why assembly, right? And the answer, I guess, was we needed it.